Welcome to our ME452 interim report, analysis, and redesign of a prosthetic. We are Team 6. My name is Scott Brandenburg.
My name is Eric Carter.
My name is Jeremy Cargill.
And my name is Anthony Potajo.
And Tej, he couldn't make it today, so it's just us doing the presentation. So for product description, the function is a prosthetic foot used to provide foot amputees with the ability to walk as they did pre-amputation. The foot is attached to the amputee's leg or prosthetic limb. Spring-loaded mechanism is used for more natural movement and shock absorption. 1 degree of freedom provides a fully mechanical system with no electronics or hardware needed. The foot is compatible with prosthetic limb or residual limb situations. The primary and secondary customers for this product are individuals as the primary customers and medical researchers as the secondary customers. Product volume, we estimate about 1,000 units per year. 800 goes to the primary customers, so 800 goes to individuals, and secondary customers being researchers, 200 goes to them. The assembly and exploded views, so we have the assembly view on the left showing all of the components in their designated places, and then on the right we have the each component and their name listed in the exploded view.
The functional analysis, basically the main point is to be able to replace the original foot. So for the first position, being able to replace the original foot, we want to allow motion. And in allowing motion, we want to be able to have the prosthetic foot support weight as well as support maneuverability. For the second function we wanted the prosthetic foot to do, we wanted to have easy installation. So we want the prosthetic foot to be able to align with the leg component, basically either the prosthetic leg or the original leg with a rod attachment, as well as shorten the connection travel distance between the prosthetic foot and the rod or prosthetic leg at which it connects to. And in other functions, we want to be able to assure dependability, which is basically we want to allow daily use. In allowing daily use, we want to have minimal vibration, as well as maintain control of the prosthetic foot when in use, allowing low resistance. We want to be able to assure convenience, enhance the product, as well as add comfort and please the senses.
So in order to determine 2 feasible assembly sequences for the prosthetic foot, fishbone diagrams were created. Both assembly sequences begin with the ankle subassembly, as the ankle base is the main component that the rest of the parts are fastened to. The first sequence then installs the pyramid frame subassembly, followed by the plantar and dorsey subassemblies, with the keel and pyramid adapter installed last. In comparison to assembly A, the keel is added to the ankle subassembly, and the pyramid adapter is added to the pyramid frame subassembly. Sequence A outperforms Sequence B in ease of locating parts and ease of fastening and joining, because the user has more room available when installing the keel and pyramid adapter at the end rather than in a subassembly. Sequence B, on the other hand, performs better in ease of transferring and handling because all of the parts are split into subassemblies. Both sequences performed in the same with regards to ease of testing subassemblies and ease of assembling in parallel, because the assemblies were assembled almost similarly. Based on the data, assembly A is the most efficient sequence with a total score of 181. To determine the importance of each part in relation to the basic functions of the prosthetic foot, a function component mapping matrix was created. The parts with the most X's, such as the keel, are important to the overall design of the prosthetic foot. However, parts with a low amount of X's are not as important and can potentially be redesigned, such as the ankle base.
In order to estimate the total cost of manufacture and assembly of the prosthetic foot, we generated a bill of materials containing all the parts and their respective material, processing, assembly, and tooling costs. These costs were generated based on the assumption that we are producing 1,000 units annually that labor is $20 an hour, and that several of the components are already available from standard catalogs. Based on these assumptions and each part's respective manufacturing and assembly process, we were able to estimate that the prosthetic foot would cost roughly $292 to produce.
For the product family design for generating for both customers, we want to be able to have the prosthetic foot support weight, support maneuverability, be able to align with the leg when connecting the prosthetic foot to the actual leg. We want to minimize the prosthetic foot's vibration, minimize resistance, as well as minimize weight. For different groups, we want to be able to assure convenience, add comfort, as well as shorten the connection travel distance between the prosthetic foot and the prosthetic leg.
So pictured, we have the primary product variant compared to the secondary product variant. The differences being that there are different springs added to abide by the functional requirement that we set for adjusting the comfort.
For the product family design for platforms, we want to have the ankle base, an ankle housing, an ankle rod, a pyramid frame, a pyramid housing, a plantar cap, a dorsey cap, as well as a pyramid adapter. For modules, we want to have a keel, a dorsey spring, and a plantar spring.
So highlighted in pink are the modules, so both springs and a keel, and these are the components that will allow for plug-in of the modules for different product variants.
Here, the product family assembly sequence for assembly sequence A is shown. For this sequence, the two product variants represented by blue and red are differentiated on the third step when the plantar subassembly is introduced. This is relatively early in the assembly sequence, meaning that it can be redesigned. The assembly sequence redesign is shown here. The plantar subassembly was moved to step 5 in order to delay differentiation so that for the first majority of the assembly sequence, the product variants are the same.
Thank you for attending our interim presentation. We hope you enjoyed.